I'm Colton Krosick. This is Exam 1 Part 1 for Carlos Coe's Transport 1 class. I'm going to be explaining the variation in air pressure and temperature assuming isentropic atmosphere starting from the basic equation of statics. We're going to assume 1 mole of gas to make the equations easier to deal with and solve, so we don't have to do any conversions, and that it'll make it easier for the ideal gas law. Adiabatic, so no heat is getting in or out, and reversible, so the pressure on the inside and outside of the system are interchangeable. So we're going to have 4 equations. We're going to start with the law of statics, which is the change in pressure over the change in height or altitude is equal to negative rho, which is the gas density, times the gravity, which is 9.8. And the second one is du equals delta Q, which is the change in heat, which will end up being negligible, minus P dV, the change in volume, and times the pressure, of course. And then number 3 is pressure, the ideal gas law, pressure times volume equals R coefficient times T. And then for 4, we have CV, which is the heat constant at a certain volume, or heat capacity, I'm sorry, and then equals the change in Q over the change in temperature, and that change in Q will be volumetric. And then we'll also have Cp equals Cv plus R, and Cp is going to be at any certain pressure. So the first kind of steps we're going to take our first equation, dP, change in pressure over change in altitude, equals negative rho g, and we're going to set that equal to our ideal gas law. And we're going to rearrange that a little bit to make it m p g, which is m is molar, the amount of moles, which will be 1, but we're not plugging numbers in, over RT. And then we can rearrange this again and get T over P equals M over R G, and we can take the integrals of these. This will be dP, and this will be dz, and this will be from Z1, Z2, P2, P1. And then the right hand side of this solves pretty easily. So we'll get over P dP equals negative mg. Did I leave a negative out of there? I did. There's a negative here in front of here. Forgot about that. Obviously, negative mg change in z times change in z over constant, and we want to find this t. To find the, we're going to want to isolate this t for the temperature equation. So then the second thing we're going to do here take our second equation, du equals delta q, which goes to 0, because adiabatic. And then minus p dv, so it goes to du equals 0 minus RT. We could plug the RT over V here in for this pressure by rearranging the ideal gas law over V dV. And then we can then play with this here fourth equation, and we can get the change in the heat capacity for a certain volume times T equals negative RT over V dV. And then we can take the integrals of both these sides. We'll bring that CV, the heat capacity of certain volume, out. This is constant. This is dt over T, and this will be from T1 to T2 equals negative R is a constant, the gas constant, dV over V. This will be from V2 from V1. And then we go to solve these integrals, and that will look like CV ln equals negative R ln V2, and that gives us T1. Simplify this to T over T1 equals V over V1 negative to the negative R over CV. And then we do some further rearranging, and we get V1 equals RT over P over RT1 over P2 to the negative R over CV. T1. And then these R's cancel out, and T's cancel out. Gives us T over T temperature, temperature 1. To the 1 plus R over CV equal to P over P1, I think. T stays, my bad. I pressed that out. To the R over CV. And then we can see this here. We take 1 plus R over CV, and that is also equal, looking at the fourth equation, that is also equal to CP over CV, so the heat capacity at a certain pressure over heat capacity over a certain volume, which will give us a ratio that is K, or also otherwise denoted as omega, or gamma, my bad, gamma. Therefore, T over T1, we can replace that, of course, so T over T1 equals P over P1. And then this will be to the gamma, and this will be gamma minus 1. And then come down here and we have T over T1 equals pressure over pressure 1 to the gamma minus 1 over gamma by rearranging simple algebra. And that gives us, this is important here, we'll have the temperature equals temperature 1 times pressure over pressure 1 to the gamma minus 1 over gamma. And that is the end of our first little solution here. We just found the temperature. And then now we take here, since we know what our temperature is, we can plug that in. So we'll have I'll show you afterwards. Temperature 1, P over P1, dP, so that'll be an integral from P1, P2 equals negative molar mass, molar amount times gravity times delta Z over R, so that's plugging that into here, this, the temperature, back into the change differential equation, and come down here and you do that, and you get T1, P1, temperature 1, pressure 1, 1 minus gamma over gamma times the integral of P to the gamma minus 1 over gamma minus 1 dP to be from P1, P2 equals negative mg change in Z. And then we can rearrange that further. It's negative mg to Z over R T1 P1 to the gamma minus 1 over gamma equals P2 P1 P to the gamma minus 1 over gamma minus 1 dp and then when you solve that integral, it gives us P gamma minus 1 over gamma. So this is between the change in pressures, between pressure 1 and pressure 2. Minus 1 over gamma. And then when you go and write that out, to find the difference, you get P2 gamma minus 1 over gamma minus P1 gamma minus 1 over gamma 1 minus gamma minus 1 over gamma times our ideal gas law, mg change in z over solve here for our P2 as P1. That'll cancel in a second here. Go to 1 minus bring that out to here, and you have to the power of gamma over gamma minus 1. So then we take back, we want this temperature equation that we found earlier, and we're going to use that and plug that into here, and we can solve for the temperature 2. So here we solve for pressure 2, pressure equation. That was not a good idea. And now using that temperature equation, you can get our work T2 equals temperature 2 equals temperature 1 times pressure 1 1 minus gamma minus 1 over gamma times mg change in z. This gas coefficient, temperature 1 over pressure 1. So these cancel, and you're left with that here. And that, the only thing that's changing here is our change in altitude. And these are our equations that we wanted to find here, that we solved for. Thank you.